Hello guys, welcome to another video. Today we'll talk about a different concept where we will see how can binomial random variable act as sum of independent Bernoulli's random variable. We'll go a little slow and understand every concept bit by bit. Before starting any of the thing, right? First, let's talk about the very basic Bernoulli's experiment. What is Bernoulli experiment? It is an independent trial with only two possible outcomes. So either it can be 1 as success or 0 as failure. You must have seen different examples like this. For example, a coin toss can be either heads or tails. If you say heads as success, then it could be 1 and 0 as tails. Or if you roll a dice and uh, run an experiment of getting 6. So either you get a 6 or not 6. Another example could be if you pick a product, whether it can be defective or not defective. So all these examples constitute a type of Bernoulli's experiment, which has only two outcomes, either 1 or 0, right? And likewise, if you put the range of x, this x variable, which denotes a Bernoulli's experiment, can only take two values, 0 and 1. And let's say if the probability of success is p, right, then the probability mass function of this particular experiment would be given as very simply as p when x equals to 1, 1 minus p when x equal to 0. So this is the simplest random experiment with only two outcomes. This is called Bernoulli's experiment. But when it comes to binomial experiment, it is little a wider concept of Bernoulli's. I would say it is a extended Bernoulli's experiment where we have more independent trials rather than one. It has n independent trials, let's say, and then we count total number of success in those n trials. For example, like we saw in a Bernoulli experiment, you toss coin one time and say there are only two outcomes, 1 or 0. Here you can toss a coin 5 times and say getting two success out of these five chances. Or maybe another example could be if you pick 10 out of 100 products, how many of them are defective and say if they are defective or not defective, right? One thing to note here that count of success would always be less than number of trials. So if you toss a coin 5 times, you can get max 5 success. So hence the range of these kind of random variable will start from 0 but can go max up to n. And likewise, if you say that probability of success of each independent trial is p, then for n trials and let's say k success, you are modeling for k success, its probability mass function would be given as with this complex formula, right? Where say n combination k, probability p to the power k, and then 1 minus p to the power n minus k. If you find this formula a little complex, just wait for some time. In the upcoming slides, we'll understand how this formula came in, and probably that would come from the concept of how can we add up these independent Bernoulli's experiment to get the binomial experiment. All right, I hope you are able to understand the difference between Bernoulli and binomial experiment. You have a basic idea about them. Now we'll come back to the main question. Can binomial experiment be a sum of individual Bernoulli's experiments? So let's start with an example. We toss a coin 2 times and count number of hits as success. So if you toss a coin 2 times, right, it can get either not a head like 0 success or 1 head in any of the chances or 2 heads, right, 2 success. So it can be viewed in two ways actually. First, either you break down these tosses individually and you can represent each toss as one independent trial, also known as Bernoulli trials, what we saw in previous slide, and name them as x1 and x2 with this probability as p equal probability, right? Or You can also look at it as a binomial experiment with true trials, with probability of p again, and then x can take any of these three values, either it will 0, 1, 2. Remember, it can go max 2. It can not exceed more than 2, right? And if you toss 2 times a coin, you can get maximum 2 hits, not more than that, right? So as you see that this random experiment can be viewed in two ways, either Bernoulli or binomial experiment. Let's break down these random variables one by one. So if the random variable takes value 0, x equal to 0, and from the binomial experiment, it means no heads. If it is no head, the possible outcome from the each toss or each independent trial would be first is tail, which is a failure, other tail is also failure. Remember, for this experiment, head is the success criteria for us. So if it is x equal to 0, it means the only possible outcome would be tail and tail, which means x1 should be equal to 0 and x2 equal to 0. And then it is easier to say that for x equal to 0, x equal would be always equal to x1 and x2. Right? So if you sum up these two values, then you will get x. Or in other words, if x has to be 0, then x1 and x2 should be 0. Then only this can be proved, right? And you have to derive the probability of x using these two. It means uh, uh, probability of x would be equal to joint probability of x1 and x2. Like uh, what would the joint probability of x1 and x2? Since these are independent trials, so we can use the independence of condition and break it down, and it will be p square. So for x equal to 0, our probability would be p square. Let's derive it for x equal to 1, right? If x equal to 1, it means 1 heads. So this head can come from the first trial, right? First heads and then tails, which means x1 equal to 1 and x2 equal to 0. Or it can come from first tail and second head, right? It means x1 equal to 0, x2 equals to 1. In any of these cases, if x has to 1, then we can easily say that x will always be equal to x1 plus x2, right? Which means if I have to derive the probability of this function, then it would be either x1 equals to 1 and x2 equal to 0 joint probability, or x1 equal to 0 and x2 equal to 1 joint probability, right? Using the law of total probability, so we can add them up. And if we just use the independence formula once again, we'll reach to this 2p into 1 minus p formula for x equal to 1, right? I hope you are clear so far. Now, if you go with x equal to 2 heads, maybe you can try driving it yourself. The possible outcome would for each independent tile has to be h and h, which means x1 and x2 equal to 1, and which will again add up to x equal to 2, right? And if I have to calculate the probability of x at 2, then it would be joint probability of x1 and x2, which would be again multiplication of these because of independence criteria, and then it will come 1 minus p square. All right, uh, which means we have to move forward. Now, if you have understood this much, then binomial, we will continue the concept and we'll generalize it. In general, for one binomial experiment with n independent trials, so if you do n independent trials and each independent trial denoted by x1, x2 till xn, with each of the probability as p success, then we can easily say total number of x would always be sum of independent random variables, which is x equal to x1 plus x2 and x3 and so on. So this is how we can add these random variables, independent random variables values to get the binomial random variable value. For example, to get two heads in 5 trials, 2 out of 5 independent trials would have to result in 1 and rest as 0, so that overall you get x equal to 2, right? 2 success. Now this can be in any order actually. You can get first two chances as heads and then rest 3 as 0, or you can get x2, x3 as heads while x1, x4 and x5 as 0, and so on. So there could be multiple combinations. So out of these five, any two can be heads, right? And that's where we capture these all possible combinations by using NCK, which is choosing any two position out of five. And that's why its PMF is actually given by NCK probability power k 1 minus b to the power n minus k. So probably you can put n and k values and reach out to the previous slide and get if you get the right answers or not. I hope this video is helpful and you are able to figure out that how can we add Bernoulli's random variables to get a binomial random variable and derive respective PMFs. All right, thank you. I hope you've liked this video.